everyone, and welcome. It is Wednesday. The crew is wise, the crew is strong. We're all gathered here, and we are in episode number 2 of From the Lab. Number what, babe? I don't know what number it is,
From the
but
lab with Daniel Sheikh.
From the
Probably number
Lab with
10.
Daniel, number 10. Wow, it's amazing. Well, we are in the middle of the group classification process. So if you've already watched the first one, you saw that we collected data points. We, as a crew, looked at the thin section, picked points, and Daniel went through with us, fine-tuned exactly where we're zooming in and collected the data. He says that was the most amazing, brilliantly entertaining, just theatrical, like it was amazing. We're on a downhill slope, guys. He says it's boring from here on out, but I guarantee we're going to make it interesting. So, no, this is good. This is the next step in the classification process. And I'm going to do a screen share. And Daniel, you can narrate however you want. I've already got the volume muted for you, okay? Welcome to the show, buddy. Thanks for joining us again.
Yeah, thanks so much, Topher. Happy to be here. And yeah, part two, we'll discuss essentially how we get the data from the software that we collected it on and then putting it on a format where we can actually start to do some interpretation. So essentially what you're seeing, if you remember, is we collected data on a data collection and processing program called Aztec or AZTech. This is run through the Oxford Instruments software, which essentially is part of the data processing that we do for all of our data collection on the scanning electron microscope and all the detectors that we use, including the EDS or Energy Dispersive Spectroscopy detector that we use to collect valuable X-ray data that we use to get chemical compositions of our minerals, which is essential for the classification process. So it's a very user-friendly program, and essentially what you'll be seeing me doing is I'm basically going to every single site. And so if you remember, we had different dots on the thin section that were pointed out by different crew members of areas of interest. And so we went to several of those areas. We collected some images. We call them backscatter electrons, like what you're seeing right there, or a BSE image. We also collected some chemical maps, which you'll see in a bit. They have a bunch of colors that, again, correspond to different mineral phases that are made up of a combination of different elements that are corresponding to a very specific color. And then lastly, we collected what are called X-ray spectra, or EDS spectra, which are just essentially getting the chemical data from a very specific spot, in this case, very small rectangles, that we put over minerals and we collect their data. And all of this is valuable for the classification process. But in this format that it's in, we can't really, I mean, we can go look at the individual data and try to make something out of it, but it's not very user friendly. It's not very easy to process this and interpret it. So what I like to do instead is I'm essentially just exporting out all the images, and I'm exporting all of that chemical data from all of the sites that we visited and all of the data points, and I'm putting it on an Excel spreadsheet. So that's kind of just simplifying everything. But there are a few things that I do in this part to ensure that we have good data. So the first thing I always do is, well, it's kind of the simple part. I just export the images. Here you'll see I'm talking a little bit about some of the data points that we collected. For example, this is a 1 point that we collected on an olivine grain, and I'm just explaining a bit on calculating the phthalate value, which is just essentially just looking at the ratio of iron over iron plus magnesium. And that's a very valuable tool when you're trying to classify different meteorite groups, particularly in the ordinary chondrites. The H, L, and LL chondrites are very known to have distinct phthalate values in the olivine, and you can use this to classify them or between them quite well. So this is just one of the tools that I'm doing. But as you'll see later in the video, and feel free to skip ahead, Topher, and just sort of move back and forth, I'm essentially just exporting images. And then once I get to the point where I will be looking at each of the spectrums that were taken from all the different sites, then I'll have to investigate them and do some data cleanup. So at that point, I'll probably have to do a little bit more narration. But in the meantime, always happy to answer questions, and feel free to have any other commentary if need be.
Cool. I do have a question because I remember the very first spot that I chose for you to take a reading from was the most contaminated spot you ever ran into. And I don't even think the reading was used. if it was used, or like where is that data now?
Yeah.
When did you rule it out?
Okay,
Exclude.
so what you're looking at is spectrum one. So site one, which is the area you chose, that had a big olivine grain in the center, and part of it was covered with this layer of carbon coating on top.
Yes.
And so when we tried to take a spot on top of it, we saw this huge peak of carbon that popped up, and that essentially contaminated the data, and we can't really use that site. But site one, which is what we're seeing on the screen right here, was taken at a spot next to the contamination. So it's actually a clean spot. So
Okay.
site one, or the spectra one, sorry, I should say, spectrum one is included in, will be included in the final data set that we'll use to classify the sample. It's a pretty clean olivine analysis.
But the first actual reading that had carbon in it, that was excluded that day and not included in your spreadsheet extraction.
So it's in there. So you'll see it's spectrum two.
Okay.
But what I do is when I look at that spectrum, it's still going to get exported. But then when I do the final data cleaning process, when I actually have the spreadsheet, then I'll exclude it from any calculations.
Fantastic. All right. Thank you for clarifying that. I was curious since day one because I knew the data was still there. The data
Yeah.
was still in the set, so I was wondering what was going on. Um, I don't know where we are in your video. Do we have any? If you guys have any questions, if you could please raise your hands and we'll get them to Sue or drop them in the chat to Sue, probably. Um, EDS, elect, no, electron data sampler. I have no idea. What is an EDS?
Energy dispersive spectroscopy. So it's a very valuable technique where you're essentially looking at X-rays that are picked up from atoms in your sample as electrons from the what we call the primary electron beam. This is generated in the scanning electron microscope by an electron source. Those electrons are fired down a column and accelerated, and when they hit your sample, they interact with atoms in it, and you form all kinds of particles and interactions. And X-rays are produced as a byproduct from the material in your sample, and you can use that as a proxy of getting the chemical composition of different things in your sample, wherever the electron beam is interacting with your sample. So if I'm looking at that olivine grain and I just want to pick up the X-rays coming from that small region, then I can just make a spectrum rectangle and pick up chemical data from that particular part, and then it'll give me that data. So that's exactly where that spectrum one was taken, was from an olivine grain. Now, some spectrum might be on different mineral phases, and this goes back to part one when we talked about we want to have very clean areas that we're taking these spectrums from, because if you're going over different mineral phases or you're going over cracks, you're basically picking up X-rays from everywhere of that region where you draw the rectangle. So you have to be careful that you're not getting contamination from two phases, or you're not going over a crack and losing a bunch of data since you're not regenerating any X-rays there. So the most important part that I always say of any data collection process and classification, whether it be through the scanning electron microscope, the electron microprobe, or any other instrument, you always want to ensure you have clean data when you're collecting it. Otherwise, the data that comes in, if it's not good, there's no way you can use it reliably for interpretation.
Mm-hmm. Okay. We had another question about the colors of the dots. I think, Cal, if you're talking about the colors on the thin section, those were just for our navigation. Was that what you were referring to?
Yeah, that is correct.
Okay. Yeah, we helped. We gave out. It's what's amazing is these thin sections. They look small until you keep zooming in and zooming in and zooming in, and the actual area that you're scanning, those squares that we were drawing, like I was amazed at how small they are. So we wanted as a crew to pick exactly where we wanted to sample from. So we just put big old thumbprints of different blotches of color to help us navigate somewhere on the slide to start with. But yeah, it was pretty crazy. The one thing I learned through the process, Daniel, was you wanted to go to where the crystal, the grain, whatever, was the most uniform and big, maybe, rather than the most hodgepodge of colors. Like, oh wow, I'm probably gonna get everything in the rainbow if I sample at this weird little spot right here. But you went for places that were more uniform.
That's correct. Yeah. The whole goal is, you can have meteorites, or most meteorites, especially most chondrites, are breccias. They're essentially mixes of many different things. And sometimes the most unique or most weird part might be this small little clast or inclusion that might be in one small area of the sample but completely absent everywhere else. And while that is good to note that it's there, if you have a certain limited amount of time to go through the sample, and as you noted, Topher, these samples look small until you zoom in and you're looking at
Yeah,
things,
like Jesus,
a
that's a whole
thousandth of
city
a
in there.
millimeter in size. Yeah, it all of a sudden becomes, how can you get all that data in so little time? And so I always try to maximize going to the most representative areas of the sample
Yeah.
and then navigating and ensuring that whether it's uniform throughout different sites when I go through the sample or if it's different. And I always try to collect data points from clean areas, but from representative areas too.
Yeah. Very good. Thanks for clarifying that. If you want to, like right there, you can see. Hold on. I'm going to go back 10 seconds, and then we have a question from Uncle Pat. So we're going to go to him next, unless you want to narrate something. But right here, you can see. Oh my God, I missed it again. Sorry. If you look at how small these sample sizes are, it's right there and right there. This is the one no, yeah. So I mean, like this is a small spot on the thin section to begin with, and then you zoom in, and like that's the sample size. So it's really tiny. Um, did you have something to narrate, or we'll pass it to Pat?
So the only thing I'd say here is that if you pay attention on the bottom left, there's a scale bar. I don't know if you can see it in this recording, but essentially for a lot of those small images, I mean, we're at things where some of those small grains are less than tens of micrometers in size, which by the way, the width of your hair is way thicker than any of these grains. So, they're very small objects, and yet we could still get good resolution on one small grain next to another small grain, so long as they're all larger than 1 micrometer in size. Otherwise, then we're getting a mix of different things.
Yeah. Now you can see the scale on there. Yeah,
Mhm.
I was hiding it. Pat, thank you.
Yeah, I just wanted to amplify Daniel's comment. So, the EDS, or energy dispersive spectroscopy, is what, by those electrons falling back to their original orbit, that's what allows us to tell what elements are there. So
Yes, that's a very key thing. Yes.
yeah, it's the mechanism for our element map.
Yep. We call
Yeah.
those characteristic X-rays. Essentially, if I guess I'll go a little more detail on that process since we have a little bit of time. So
Yeah, man.
when electrons from the beam interact with atoms in your sample, you can get two primary interactions that I'm documenting when I do the classification process. The first is those grayscale backscale electron images. That happens because the electrons, depending on interactions with the nuclei of different atoms in your sample, depending on how many protons you have in that nucleus, which if you have materials that are rich in metallic, like metals that have a lot of iron, a lot of nickel, you're going to have some big nucleus because they have high Z values. So those electrons are going to more than likely be elastically scattered back upwards, where they then get picked up in the detector. And depending on the intensity of how many of those electrons that have been backscattered have been picked up, that correlates to a signal, which correlates to essentially a black and white contrast value from 0 to 255. And so the simplified way to explain this is that a backscatter electron just can tell you the average Z value in your sample, which essentially means materials that are rich in high Z elements like iron, nickel, cobalt, like metals, are going to shine as bright white. Troilite, which is going to have iron and sulfur, is going to be also pretty bright. And materials that have, elements with low Z phases like sodium, potassium, even in some cases silicon, magnesium, they're going to be darker. And so you can use this as a tool to identify different minerals just based on their average atomic number. It's not perfect because different minerals, of course, can be zoned, meaning the concentration of elements in one point might be different than everywhere else, in which case I'm using these chemical maps to differentiate them. And the way these come about, and as Pat explained a little bit, is that the other interaction you get are when those electrons actually can knock off secondary electrons from the electron orbitals or orbitals in your atom. So essentially, if you envision the atom as having a nucleus and different electron shells that go around it, if those primary electrons from the beam can knock off some inner orbital electrons from some of the closest ones to the nucleus, outer shell electrons will try to fill in the place. This is called trying to maintain equilibrium. And as doing so, it releases this burst of energy in the form of an X-ray. And depending on what element you're looking at, these are called characteristic X-rays that then can get picked up in our X-ray detector, and they can tell you exactly what element is being picked up. And you can use this as a proxy depending on the energies of these X-rays to tell you what elements are from wherever you're scanning from. So to simplify that, all that means is that we can go to any point of interest on our sample, we can get data, and it'll give us the energy spectrum for all of those characteristic X-rays and background X-rays that are picked up from that area. We then process it through the software, and it can basically pick up different energy peaks, assign those to different elements, and say you have an iron peak right there, you have a magnesium peak here, you have X concentration of magnesium, X concentration of iron, based on how many of those X-ray peaks you pick up, so the intensity. And then it basically spits out a final number that says, based on your energy spectrum that you have at this interest, at this area, and what elements are in here, this is their concentration. And then you can use that to assign things to like what mineral phases have what element concentrations in them. And there's different ways you can show the output. So that's really all we're doing here. We're just getting backscatter electron images for viewing textures, looking at mineral phases, the chemical maps to identify mineral phases, and the EDS spots to essentially get chemical data from the minerals. And we're just extracting all of that to a spreadsheet.
Fantastic, man. Appreciate it. Oh, we got Mike Kelly with his hand up. Welcome to the
Evening,
show, Mike.
Daniel. Hey, thanks. So I had a question for you, Daniel. You mentioned, you want to get representative sample sizes for the material that you're looking at. So I know like you're interested in lunars and things like that, some of the things that are polymicted in nature. So like say this sample that they had is polymicted in nature. How many samples do you need per lithology to really kind of dial things in? Because like I said, time is precious when you're on the SEM. So what are sample sizes look like for something like this?
Yeah.
Yeah, no, Mike, that's a great question. It's very important. Obviously, we analyze thin sections, so obviously you have to first take those samples and then turn them into thin sections. But it's very important to know what material you are going to look at. So the first thing I always do is I try to see images of the whole rock as best as I can. Just images of slices. And just try to see, does it look the same on different stones? If it's one stone, is it like, are there two lithologies? Is it split up in different things? Is it mostly one lithology and then there's like a small inclusion of something? Those are all important to know. If I know it's something that has like, multiple pieces and some of them look like one lithology and some look like another one, then I'll need representative pieces of both. I had this in the case of Erichides 004, right? There was a high metal and low metal lithology that clearly looked different and needed to both be sampled. I've also had cases like with lunar samples or even HEDs where, I have this one large like gabbro clast that was pretty big, and then it was in this sort of this polymic like impact melt matrix. But because of how large the gabbro was in that meteorite based on everything else, it's deserved sort of its own, study. So I sort of had a thin section made of that and then a thin section made of the host matrix. So really it depends on the sample. Like if it's a noteworthy inclusion in like a polymix spreadsheet that's like very large, or if it's distinctly between many different pieces, they don't all look the same, then it's worth investigating by getting multiple pieces.
Thanks.
Well, right on. Thank you very much. We had a question in there. Maybe Cal, excuse me, Cal, do you want to ask your percentage of oxides question?
Yeah, I can do that. You had mentioned, talked a bit about the total oxide percent should add up to 100. And you say, and he gives some reasons why it might be less. Is there a lower limit of what might make it acceptable or unacceptable?
Yeah, that's a great question. So the thing is that the oxide percent is very important, but it's not as important in data collection using the EDS as it is in using a technique with the electron microprobe. So essentially, ideally, in a perfect world, you want all your totals to add up to 100%. But as it turns out, in some cases, you don't get exactly to 100%. You sometimes get like 99.5. You can sometimes go with 100.4. With the electron microprobe, ideally, you want to have totals that are anywhere from 98 to 102%. Ideally, the best would be the ones closest to 100. When you're the reason why it falls off a little more when you're using a scanning electron microscope is because your your current, or essentially, which is what you're a key factor when you're doing something like the electron microprobe analysis, your probe current is at a fixed value when you're doing EPMA. When you're using a scanning electron microscope, your probe current is a lot lower, and that has a huge influence on what your range could be on your oxide percent totals, believe it or not. And so what happens then is that you can get like analyses that are very clean and good mineral phases that have really good, and I think I talked a bit about cation sums. So the stoichiometrically they're perfect, but their totals are just lower, and that's just because the beam stability during the data collection process is not as stable as it would be on something like electron microprobe, where for that they specifically fix it at something like 20.00 nanoamps, because that's more for quantitative data collection that instrument's like tailored for. For here, the main thing we focus on is, are we getting a clean data spectrum from a mineral phase? Are the cation sums clean enough that we can essentially fit this with a stoichiometric mineral? And the totals, if they're between, like, if we analyze 10 olivines and the totals vary from 92 to 94, or or something like that, but they're all clean olivines, I'm not so worried about that. In some cases, we have normalization tools to like normalize that to 100 if we need to. But what I am more concerned with is if I hit a phase and I'm getting a total of, let's say, 60, and then I hit another phase and I get a total of 90. The phase that probably has 60, even if we account for errors, that probably is still very low, and likely something like a hydrous mineral phase, like a phyllosilicate, or an amphibole or something. So it depends on the technique you use, but I try to focus on using atomic percent and just looking at the cation totals more so than focusing on oxide weight percent, which is typically done with electron microprobe.
Thank you.
Right on, Cal. Thanks for joining us, man. Um, Here's an extra bonus for those that are in the classification group, and I guess for anyone here as well. Normally during the classification process, you don't see this stuff, obviously, and you don't get copies of this. Well, I actually have a copy of this spreadsheet. I won't tell you how I got it. I'm pretty connected, but I think it's cool because all the images are captured on it, all the data is captured on it, and I think it's a really, really cool thing to dig into. As you're watching this video, you can have it there with you and scroll through it. Pretty interesting. We do have Anthony with a question, I think I was told. Anthony, are you with us?
I am.
Nice.
I just had a question about the software. If like who makes it? Is this something that's specific for classifying meteorites, or is this something that you would find like in like a geology lab?
Yeah, that's a great question. So this is run through Oxford Instruments. So they essentially are the manufacturers, behind a lot of the different detectors that we have. So they essentially, manufactured the EDS detector that we have, and therefore they have this software tailored to whenever you're using that detector. They have several other processing softwares as well, depending on if you have different detectors for the scanning electron microscope. There, of course, are other there are other tools you can use. So like there's other programs run by other organizations, like, let's say if you were using a Zeiss electron SEM that has a let's see, there's Yeah, there's another program. I'm trying to remember the name off the top of my head. I used it a few years ago, but there are several different programs that you can use. This isn't the only one. But what's good about Aztec compared to using other SEM data processing softwares when you're collecting images is that it's all collected in sort of this live time where you can collect an image, you can store the image, and you can collect the sites and store those. A lot of other programs sometimes when you collect the data, sometimes you have to export them separately and you can't have them all in one place. But you can take this whole, this data sheet essentially on this software and you can send it to someone else. They're pretty big files, but you can send them to other people and they can open it. And as long as they have this software, they can see everything, and do all the exporting from there. The only thing I will say is that you do need a license to get the Oxford Instruments software package, which our university has an agreement with them. They have the license for it because we have the instrument. Not a lot of geology departments that I know use Oxford Instrument detectors on their SEM. Some of them use different ones, but I have to say, from using different uh, processing softwares, this one is my favorite, just because it's very user friendly. Like as you can see right now, I'm essentially looking at the energy spectrum, for the different areas that we went to, and I'm just doing some data cleanup. So I'm trying to fit elements to different energy peaks, and this isn't something you can really do on other programs very well. This is something that's like really good with this particular software. So I would recommend if anyone does purchase a scanning electron microscope in the future to
Yeah,
get the Oxford Instruments detectors.
that's awesome. Anthony, thank you for asking that. You brought a laugh to my face with that, that answer, Daniel. I have a question about the gray scaling. You were talking about a 0 to 255 level, and the more metal or oxides, the lighter the color. What about that's free metals, or is this total metal? Because I know in a reading of a meteorite, you have two different metal contents. You have the free metal and the total metal. Can you talk to that and what we're seeing and how it's displayed in these grayscales, if we can see that?
So yeah, so great question, Topher. So I believe what you're referring to are the distinctions that are normally assigned, I believe, with the ordinary chondrites and other samples of things like total iron versus metallic iron. So metallic iron, we're concerned with iron, the element that's in what's called the reduced oxidation state, which means it's iron and then it's like Fe and then like a zero. That means that the iron is metallically bonded with other elements like nickel, and you form these metals. So that's what metallic iron refers to, the abundance of how much of these metallic phases are in your sample. But the other thing that you might come across in the literature is something called total iron. And that's when, let's say, they measure like a bulk composition of an H chondrite or an L chondrite or an LL, and you see how much iron weight percent is in there. That's essentially accounting for just the total amount of iron that's in the sample in all oxidation states, whether it's in metal, whether it's in silicates, in which case it's either in the plus 2+ state. Sometimes you can have alteration phases, and then it's in the 3+ state. But that's just saying this is all the iron that's in your sample, no matter the oxidation state. Metallic iron is only focused on iron that's in the reduced oxidation state to form metals. That's the difference.
Okay, thank you. Appreciate that.
So there is one more thing I will say on this. So you'll notice how I'm going through each of the, so what I'm doing at this point is after the images are exported, I'm now going on every single spectrum from basically every data point we collected, and I'm checking each of them and I'm removing any random elements that may appear. So you see I'm removing carbon a lot. That's because several of the spots did have carbon, but it wasn't that much to make an impact. But if you don't remove it, it kind of still shows up in that element list, and I don't really like that, so I remove it. The other thing that I tend to look for are sometimes you have random, like elements that pop up. Like you might see something like scandium pop up. You might see something like vanadium or like cobalt. Those aren't really elements you can measure very well from the minerals we're looking at, just because they're in so low concentrations that you're not really picking them up. You're more so just picking up some signal that just the system doesn't really, it can't really, you know, tell the difference. It just says you have a little bit of it in here, but we know from the mineral phases we're seeing, those don't exist. And so I'm just removing those essentially extra or extraneous elements that we don't need. But I have to go through every single spectrum to do so and
Yeah.
check. And if you don't do that, what accidentally can happen is that when you eventually look at the data and process it, sometimes it might add a certain like amount of some random element that doesn't exist, and it will actually throw off your calculations of several values. Not too much, but just a little
Yeah.
bit. So just to avoid that altogether, I'm just making sure each of the spectra that comes through has the same elements and that they're all clean. So yeah, right there, you can see I'm removing mercury, I'm removing some other phases. Those might be present, but in very, very small concentrations that we can't really pick up with this instrument. So that's why I'm checking.
And would those elements add to your classification at all, or is it really just so extemporaneous that it doesn't matter because we're looking at something else entirely?
Yeah, I mean, it could. So, like for example, I'm looking at those two peaks you see on the left. The left one is called the iron K alpha peak. The peak on the right is called the iron K beta peak. So these are two energy peaks that we pick up for that are characteristic of iron in our sample. But in the middle, there's a small peak where the cobalt K alpha peak interacts with the iron K beta peak. And because using EDS, we can't distinguish the two because our spectral resolution is not very good. That's a technique where you have to use the electron microprobe. So if you're looking at something like an iron meteorite and you're trying to look at how much nickel or how much cobalt is in it, we can't do that using EDS, unfortunately. You have to use an electron microprobe. That also means that if you're trying to look at things like, you know, how much like gallium, germanium, all those important siderophile elements in iron meteorites that people try to use, you know, to classify them depending on the different iron meteorite groups. We can't do that with this technique either because they're in so low abundances and there's many overlaps between all their energy peaks that we just can't pick them up with this technique. So that's kind of what I'm explaining there, is that there are limitations to any data collection technique. And our limitations are the peak overlaps between energy peaks that are too close and energy peaks that we just don't have high enough intensities to pick up because the element concentrations are just too low in our samples.
Wow, that's really cool. So a classifier of iron meteorites will be using a different tool set than you because you guys are really looking for the different elements at a different range, and also with the metal, I would imagine they're so similar in how they react that they would overlap each other quite a bit. But I haven't
Yeah,
taken.
anyone who's looking at iron meteorites, what they're doing is a completely different process. They're essentially just taking apart an iron meteorite, dissolving it in acid, and then just measuring trace element concentrations, which are at, so for reference, the lowest detection limit that I can get for an element, you know, with pretty good accuracy or precision, I should say, is probably about 0.1 weight percent. Whenever you're looking at trace elements, they're looking into the parts per million, you know, parts per billion range, which is way, you know, at least 3, 4 orders of magnitude lower than, you know, what I can pick up here. So there's different limits for different instruments.
Very cool.
Yep, and then what I'm doing there is I'm essentially just putting all of the different spectrum, I'm putting it onto this, essentially this large view window here, and I'm just making sure that all the elements that you see listed, so going from oxygen all the way to nickel, that they're all, you know, correct. We don't have any random, you know, elements that are in there. I'm making sure they're in atomic percent. That another way of saying that is molecular percent. This is really good when you're trying to do any kinds of stoichiometric calculations like phalite, frostite, blastenite, you know, anorthite number you see in lunar meteorites, HEDs, iron manganese ratios that you see very commonly when you look at methyl submissions of achondrites. This is just the easiest way to do the interpretation and the calculations. But I also export it in other formats too. So you can do elemental weight percent, you know, oxide percent. But I'm just putting it all in one place where I can then transfer it over to the spreadsheet.
Wow. 66 sites were sensed. That's crazy. Like I don't know. I guess when I got into this years ago, I think, oh, testing a meteorite, yeah, you're going to zoom in on this little. Well, actually, you're going to zoom in on this little thin section and maybe take 10 readings, and if you're lucky, you're there's so much real estate on these things. Like I would, that's the one thing I keep on saying, but it blew me away. You just keep on zooming in and zooming in and zooming in. Like, where do you want me to take the sample from? It's like, geez, 10 screens ago.
Yeah, one of the benefits of the technique that we use when we classify using the EDS and the SEM together is that the electron microprobe, although it being traditionally used as sort of the default instrument for classification back in the day, and even still nowadays for some people, it's very limited. It wasn't exactly designed for having good spatial resolution when you're zooming into your sample. So whenever you zoomed in, everything kind of was a little blurry, and you had to sort of rely on going to a nice area to get a data point from. With using the SEM, you can go down to almost like tens of nanometers, like very very small objects, and you can get pretty crisp images of them. So obviously for geological needs, getting things at the micrometer scale is very easy to get nice images of. And the other thing that is pretty cool about using EDS is it's much faster. With traditional microprobe techniques, you're essentially have to wait, several minutes, probably mm, about 4 minutes, I'd probably would say per point. And you
Hmm.
have to navigate the stage, like so you have to move the sample into the crosshairs, and then you have to sit there waiting for like 4 to 5 minutes while it collects data from one spot. With our technique, you can show this large area that looks very clean, and then you can just put rectangles over each of them. So you essentially move the beam to the sample rather than the other way around. And that makes it where you can get, depending on how long you set your counting times, you can get way more spots a lot quicker. And so in probably, I think we went for maybe 3 hours and we got 60 sites. That's probably, yeah, I'd probably say like that's pretty good. In some cases, even within an hour, I can get about like 40 to 50 sites, which is a lot faster than if you're using a microprobe. So you get more data out of it at
Yeah.
the end of the day.
God, you'd be sitting there just twiddling your thumbs for a couple hours waiting for the reading. Yeah, it was amazingly quick, and it was really cool to have the entire thing on screen and then be able to. It's like only thing I can liken it to is like a Google map. You download the entire map and it's there, and you can zoom into whatever street or address you want, put a flag there, and then zoom back out and pick another spot, and then say navigate. And that's kind of what my impression was we were doing.
Yep, that's exactly what it is. Yeah, it's very interactive, a lot more user friendly, and you're not just selecting points and then you have to wait like 50 minutes as it collects the data and you're just like sitting there. You're actually moving around and navigating. So there's a lot of interactiveness with that process.
Yeah, that's awesome, man. All right, so now you have all this stuff. You export it into a
Yep.
spreadsheet. Is that the next to final step, or
Mm.
boom?
Well, it depends, but yeah, so that would be part three. So part three is okay, now we have all the data on the spreadsheet. So how do we actually get like a phaolite value? How do we get it
Mhm.
out from all that data? So part three is basically me just which I'm going to do in live time. I think I think the recording is not the best way to do that. So
Mhm.
I'm basically just going to be going through, processing the data mineral by mineral, making sure they're clean, and then calculating phaolite. We can all do that together, calculating frostlight, and then
Mhm.
just going into, the write-up and saying, okay, what meteorite group do we have? What is
Mhm.
its, shock stage, weathering grade, petrologic type, who owns this mass, who owns how much, and I'll be taking that from a Google Doc that I believe several members have access to. So I'll take that information, put it on there, and then I'll just hit submit, and it'll go right to the nomenclature committee in lifetime.
Wow, that's
Yeah.
awesome. We'll get into this a little bit. Well, I don't know if it's going to be something we do next week or next time or not, but the external description of the stone. That's kind of something. Is that something that you do, or can we do together,
You
or?
can do all of that. So physical characteristics, anything on the history section, any cool things you find in the stone, anything really, as long as it's included in sort of the description, like a paragraph or something, I could literally just copy and paste it onto those sections. So
Beautiful.
if there's anything you have in any of your pieces that, that at least, like, for example, if you own 5.4 grams and there's like a interesting inclusion or something you want to mention on there, definitely you can do that. The only sections that I'll have probably the most control on are going to be the petrography and the geochemistry section. But yeah, the anything else that describes like any external features on the sample, if you want to just talk about it, go ahead. That's all for you to do that.
Nice. Fantastic, man. Yeah, I actually have pictures and video of the entire stone, uncut. So we'll have to do that together. I think Sue is working on some narrative about writing the knowledge bolide and our mission and our goal with this classification. This may be if this classification gets rejected by the nomenclature committee, it's not because of anything you did. Yeah. Well, we appreciate your partnership on our channel. We really do. I know that you got you increased your YouTube subscribers by 50% since our last time having you on there. But that's only 100 people. We need more. We need everyone who's watching this video. It's over now. We're gonna log off. Go to Daniel's channel and subscribe. And it's in the description below, so you can just literally just click as soon as we're done. Daniel, thanks a lot for joining the crew. We really appreciate your partnership, as I said. Thank you very much.
Thanks so much, Topher. Appreciate it as always.